All right, and welcome back. If you came from part one, we're just going to dive right on in. If you didn't see part one, go ahead and check it out real quick and then come back. There's a lot of setup in order for this video to in order for this video to make sense. And what we left off on in that video was the question of whether or not our irrational slope solutions to the original system fill the torus. Like they do live, the solutions live on a torus sitting inside of R4, but do these solutions necessarily fill the torus? And it turns out no. For some figures, no, that's not the case. They're only going to fill a part of it. They're only going to fill in a knot's worth of solutions, or a knot's worth of points on the torus. But for others, we're making the case here that it's entirely possible for us to fill a two-dimensional object with a one-dimensional curve. And that should bother the living hell out of everyone. These are just fundamentally, topologically incompatible elements. How could you use something one-dimensional, which has zero length, zero area, sitting inside of a two-dimensional object? How can you use something with zero area to fill up a non-zero amount of area? That should be very disconcerting. So what do I even mean by fill the square? Like, what does that even mean? And in order to understand this, we're going to start to use some tools that we've developed over the past few weeks. And here's how we're going to go about studying this one. We would like to appeal to a Poincare map of the orbits. Right, specifically a Poincare map of a particular irrational slope orbit. And the cross-section, or the Poincare section that we're going to use here, is a meridian curve. We're going to use one of these blue curves. And we're going to reimagine this question in terms of the Poincare map. So we could also use the longitude and get similar findings, but it's easier for us to visualize what's happening on the blue segment, I think. So for a rational slope, right, the P and Q equals 2 and 3 that we did before, we had two intersections. So if I go back to that torus here, check it out. It's happening right here. You're asking, where does the green curve meet the blue? How many times? And it looks like it only meets it twice. And that's no coincidence, right? It's exactly the P that we saw from before. So this curve is only going to intersect the Poincare section twice, ever, right? Or it's only in those 2 points. It will just keep cycling through them forever. So this is exactly what we see on that circle, that we only get the 2 points, and they keep cycling between each other. You start at x of 0 on the right here, and then it cycles over into x of pi, then back to 2 pi, then 3 pi, and so on. It just keeps flipping between the two. And we have a nice 2 cycle. Right? If we had p equals 5 and q equals 3, on the other hand, we would notice that we're going to start at x0 and then go 1, 2, 3, right? That's q. We're going 3 spaces over to get the next element of the sequence. And then we go 1, 2, 3 to get the next element of the sequence. And then maybe do this one in yellow. 1, 2, 2, 3, and that'll get you the next element of the sequence, and so on. But the point is that we still wind up with periodic behavior on the Poincare map, and it's associating with these periodic orbits. Oh, come on, work with me. But the trick in general is that for a rational slope of q over p in lowest form, or lowest terms, then the Poincare map is also periodic, and it has period p. So if the slope is not rational, we ask the following questions. We pose the following proposition, that if we have an irrational slope, then the map, the orbit of the Poincare map of any initial condition is actually dense on that Poincare section, and in some sense fills the Poincare section. Just like our orbits are going to fill up the torus. Our curve is going to fill up the torus. So in order to know what I mean by dense, I have to give you a definition. And this is exactly what we're going to do. Right? So I'll tell you that a sequence sitting inside of a set S is dense in that set S if for each tolerance level epsilon and every point in S, there is a point, there is a time in the sequence, there is an index in the sequence where the difference between xn and S is less than epsilon. So in other words, the sequence can get arbitrarily close to each point of the set S. That is not to say that the sequence passes through every point of the set, right? It just says that we can make an arbitrarily good approximation of each point in the set by using some element of the sequence. Okay, so this is a very technical definition, and I will remind you that we have seen something like this before, that the rational numbers are dense inside of the reals. In fact, this is, in some circles, how you define the real numbers, that it is the closure of the rationals. But I digress. We're going to use this definition as part of our proposition. We're saying that the Poincare map, or the orbit in the Poincare map of any initial condition when we use an irrational slope is going to fill that circle. We can get arbitrarily close to each element of the circle via some element of the Poincare map sequence. So let's see how that works. So if I come up to the top here, proof of the proposition, we're going to go ahead and let P denote the Poincare map. And this is going to be for the flow that we defined upstairs, and it's going to happen on the torus. This is all just setting the same stage for before. It's all just kind of a technical way of writing down all of the geometric intuition that we laid out upstairs. We are going to choose any point, right? Any point x0 on the meridian curve, or specifically on the Poincare section, and we're going to define its orbit sequence as we do before. It's the first return map, so if I follow this curve, yada, 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 that guy follows back right here. So this is x1 of the sequence. Okay, so come on, work with me. And 2, 1, and go. Cool. So it's the same setup for a Poincare map as before, and I'll give credit for the picture here to the textbook from Hirsch, Smale, and Devaney. It's a nice figure, and I didn't want to stomp on it. It's a good picture. So let's go ahead and give ourselves what we need from the definition of density. We're going to need an epsilon and our starting point, or we're going to need some arbitrary point, little s, in the circle. So for any tolerance here, so let epsilon be that tolerance, there must be some pair of points, xm and xn, in the sequence, such that the difference between these two guys, such that these 2 points are within epsilon along the circumference of the circle. They are within epsilon units of one another. In other words, otherwise, what would happen if that wasn't the case? Well, that means that each pair of elements has to be at least epsilon wide, and that would mean that my sequence, which necessarily has infinitely many elements in it, all of which apparently have to be at least epsilon away from one another, would imply that the circle would have an infinite circumference. That's not right. So that means that these guys, there has to be at least one pair of elements that gets within that epsilon. So we can actually go ahead and take this pair and shift it back so that m is actually at 0. So we're just going to kind of pull the orbit back a little bit by m. And we shift back by m iterations of the Poincare map and find that this element xn minus m is actually within epsilon of the initial condition x0. And we're going to use this kind of as a fundamental building block of a covering, where we're going to go ahead and cover the circle with elements, or with segments, or what would they be? They would be arcs. We're going to fill in the circle with these arcs of length no greater than epsilon. So notice that these intervals, and these intervals are, again, they're arcs on the circle, these IKs, and it's just telling you how many times you have to iterate through to get to the next element of the sequence. So to get to the next guy that is epsilon away from the previous. So these intervals are going to build a cover for the circle sigma. So each point in S has to live in at least one of these intervals for some k. So for each epsilon and point S in sigma, we can construct that cover, put little s inside of one of those elements or inside one of those intervals, and then we would have a pair, our choice really, of either xk times n minus m or xk plus 1 times n minus m as being some element that is within epsilon of that s. So that means that the orbit here, xn equals, or the Poincare orbit, is dense. We can get arbitrarily close to any element on the circle via this Poincare map, or some sequence based on whatever initial condition x0 we wanted. So the answer is, from our initial question of, does this curve ever close up? Well, yes. This curve, not do they close up, the question about whether or not this curve fills the torus, and the answer is yes, but with a certain caveat that we need to make sure we have an irrational slope for that curve, and that we need to make sure that we know that we're getting arbitrarily close to these points and not necessarily passing through them. So the trajectories do fill the torus in terms of density. So this orbit is dense inside of the torus. Again, it doesn't necessarily pass through every element of the torus, but it does get arbitrarily close to anything in the torus, any point in the torus. So now comes the question here. Since we have this weird bouncing around of like this Poincare orbit might be a little tricky to decipher. I mean, should we consider this chaotic dynamics? It's like, does an irrational rotation correspond to chaos? And well, remember, we want our definition of chaos to, at least colloquially, mean a wandering deterministic system whose long-term behavior is practically unpredictable. And our system, our irrational rotation dynamics, are so close to this. They do wander in some sense. They are aperiodic, right? They do not return to where they started. They are still deterministic. There's nothing random about this system. The thing that fails is the long-term unpredictability. Turns out that all the dynamics here are kind of parallel to one another. The solutions that start close to each other never deviate from each other. So think about it this way. If we had a pair of solutions and we map this guy out for a long time, 200 pi is what I have in this picture. Let's start out with the original picture that we had in blue, right? That we had this this apparently filling Lissajous figure. And we're going to go ahead and zoom in so that we have a blue initial condition that is very close to, but not quite the same as, the original figure or the original system. Then what we actually wind up with is a set of parallel curves here. And this, if I'm zooming in correctly, this almost looks like a plaid shirt. It's kind of interesting. I didn't notice that before, but that's kind of awesome. But the point is that these dynamics are actually parallel to one another. Right? Again, they can never intersect due to uniqueness of solutions. But more to the point here, these solutions are basically the same. Right? If we start at a point that is very close to, but not equal to, the original initial condition, then we actually just get dynamics that are offset by a fixed amount for all time. So we fail the third criterion here because we can actually predict what happens in long term. These solutions, if we're off by a little bit, do not deviate in the long term. They are the same distance apart for all time. So no, we should not consider these guys to be chaotic. So what should we call them? Well, kind of a fun little thing you can do on MATLAB just for yourself. You can show that these guys are kind of periodic. They're very close to being periodic, but they're not quite. And you can see this really well if you plot something like this figure downstairs. Right? If you use sine of 3t plus sine of pi t, right? The ratio between pi and 3 is most assuredly irrational. And that means that we have an irrational rotation dynamic, or we exhibit irrational rotation dynamics. And this creates something that looks like it's following some amount of periodicity. It's trying really hard to be periodic, but it can't be. And I want to draw your attention to these transition spaces in the middle. Like, these guys are very irregular. They don't do the same thing on every transition. And this is exactly why our system is not periodic. Like, they're shifted by a tiny bit every single time. So what we are going to call this kind of dynamics, it is irrational rotation dynamics, but the kinds of solutions, or the feature that's captured here, is something we're going to call quasi periodicity. Right? And this is where we're going to leave our old analysis of dynamics behind and say we have figured out just about every kind of dynamics that we can talk about in the smooth setting up to this point. Like, we've discussed everything that could happen, and none of it is chaos. So what we're going to do in the next video is actually define rigorously what chaotic dynamics need to look like, or what the most commonly accepted definition of chaotic dynamics is at present. Right? And again, it's a very touchy subject, which is why we went through this entire almost hour-long exposition of figuring out what chaos isn't, in order for us to figure out how careful we need to be in our definition